It's the opposite way.
It's a little weird. Hello, everyone. Welcome. We're gonna wait a couple minutes while folks start getting on here for today's experiment along. I'm Dr. Shannon. I'm the director of the Abrams Planetarium.
I'm Veda.
This is Veda. She will be helping me out today with today's experiment along. This is my daughter. She is 7 years old. So she just helped me do a quick run through. So we know that a 7-year-old can help out. We are going to probably have some appearances by Veda's younger 2-year-old sister, Thora. So if you see her pop in, you can say hi to her too. We're going to give it a couple minutes just for people to filter in while we do. We haven't made official events for them, but we do have more experiment-alongs planned. So we are going to have one next Monday with Kristen. She's going to be talking about light and doing things with CDs so that you can look at the spectrums of lights. And then the following Monday, we're going to do one about spinning experiments. So if you have fidget spinners, get those ready. And if not, we're going to have plenty to do without fidget spinners as well. So check those out.
I'm going to grab something.
Okay, you go grab something. And then we're also going to be having Celestial Story Time. We've got the next 3 picked out. So tomorrow morning at 10, we have Amy Jackson joining us. So she is the author of the story that is going to be read. It's called Cassandra in the Night Sky. So she'll be joining us from Texas to read her story. So we have the author reading her own story. That's very exciting. And then we have Ada Twist, Scientist, with Rebecca on Thursday. And Here We Are, a guide for living on planet Earth with me next Tuesday. So join us for those. All right, go ahead and put your comments in the comment box. I should be able to see them, but we're gonna go ahead and get started. Are you ready, Veda?
Mm-hmm.
All right, so today we're going to be talking about the expanding universe. So maybe people have heard this, that the universe is expanding. So what does that mean? Okay, we're not gonna play with that right now. So the universe is expanding. And so what that means is that on a smaller scale, astronomically speaking, gravity can win out. So gravity will pull things in together. So on the size of the solar system, we are attracted to the sun and we orbit the sun. Within the size of our galaxy, the Milky Way, we orbit around the center of the Milky Way, and gravity, it wins out. But on a much larger scale, so in between these big groups of galaxies in our universe, there's something that's actually pushing space apart. And so when we look at really far away galaxies, we can see that the universe is expanding. So we're going to do an experiment with a balloon. So this is a model of how the universe is expanding. And so it's going to show us how we know that the universe is expanding. And I'm going to talk a little bit afterwards about the types of observations that we make in order to show that. So if you have a balloon, go ahead and get the balloon. I've also got this board back here that we're going to keep track of things. You don't have to keep track of it if you don't want to. You can just do the balloon part, but I find it handy in order to write things down. No.
Chalkboard.
We do have a chalkboard behind, but we're going to use the whiteboard side today.
Okay.
So we're going to have some different galaxies, and we're going to measure their distances a couple of times. So this is a good way that scientists help keep track of the data that they're gathering. So that's what we're going to be doing today. All right, are you ready, Veda? So what we're going to do is we're going to get our balloon, and we're going to blow.
I want to do it.
I'm going to blow up the balloon. You're going to help me draw on it, remember?
No, you draw.
Okay. You can try to blow it up.
I know how.
Okay. Blow it up just a little bit.
It's a little hard, but
Yeah.
I can.
Oh, there you go. Good job. Now hold it really, really tight. Don't let any of the air out. So now go ahead and get a marker, and we're going to draw a little dot on it. sort of near our hand, and we're gonna label it. Don't let any air out. Okay, bring it down so I can see it. And we're going to label it MW to show off the Milky Way. So can you show them in the camera, Veda, where I labeled Milky Way? All right, so Milky Way. I guess you could read it either direction and it still says MW. Okay.
Let out a
Okay, so now let's not let out anymore. Now we're gonna put 3 dots at different distances from the Milky Way. We're gonna have dot 1 that I'll label A. We're gonna have another dot a little bit farther away that we'll label dot B. And we'll have another one even farther away that we'll label dot C. Look, I kind of made a triangle with my galaxies. So now what we're gonna do is blow up the balloon for another, oh wait, no, not yet. I forgot a step. Okay, so now what we're going to do is measure the distances from the Milky Way to these galaxies. So this is going to be the first distance. Okay, so I'm going to use this measuring tape that I use in sewing because it's nice and flexible and can go over the balloon and wrap around it. If that doesn't work for you, you can get a piece of paper and go over it and mark how far away it is. And then you can get a regular ruler and measure it that way. That also works. So I'm going to use the centimeter. This one has both inches and centimeters on it. I'm going to go ahead and use the centimeters because that's a unit of measurement that scientists would use more often. It's a little bit easier to use and it's got smaller units, so it's going to be a lot easier to measure things on these scales that we have. All right, so I'm going to take this real quick, baby, and we're going to twist it up. And now you can hold it really tight so it doesn't let any air out. Okay. So I'm going to measure from galaxy A to the Milky Way in centimeters. And I see we are about 3 centimeters away. So I'm going to go ahead and write 3 centimeters. I'm going to have you move so they can see. Galaxy A, our first distance is 3 centimeters. Now we'll do the same thing for galaxy B. So I'll measure from the Milky Way to galaxy B. And I see that is about 5 centimeters. 5 centimeters. And now finally, we'll do that for galaxy C. It is really helpful to have 2 people to do this, but it is possible to do it with 1 person. All right, so I see that A to galaxy C is about 8 centimeters. So that's the first distance. Now we're going to blow this balloon up more. All right, are we ready to blow the balloon up? We're going to blow it up for 10 seconds. So Veda's going to blow it up, and I am going to count to 10. Are you ready? All right, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, hold on to that nice and tight. It took us 10 seconds to blow up the balloon. I'm going to write that up here. All right, so now we're going to measure the distance again. So, all right, can I take the balloon real quick? So here is our balloon. So there's our Milky Way, our A, B, and C. Do you see that our shape right here is still a triangle? It's still the same shape we had before. So, oh, hello. It is very fun to play with. This is a very silly universe. Now, we can see that A, B, and C still make a triangle, but the space between them grew. The universe, the balloon universe, expanded. So now let's see. Right. I know, it's so silly, isn't it? All right, so let's measure this again. Beta, can you come help me? Okay. We are going to now measure the distance between the Milky Way and galaxy A. It is now about 4 centimeters. So I will write that down. See, you can do it with 1 person. All right, now let's do it between galaxy Milky Way and galaxy B. That is about 7 centimeters. So let's write that down. Okay, Beta, I'm trying to show people things. All right, and then finally, the Milky Way to galaxy C is about 16 centimeters. So 16 centimeters. So what we can see here is that in that time, the shape stayed the same, but the different galaxies moved away different amounts. So the first galaxy, I'm going to write the difference down here. The first galaxy only moved 1 centimeter farther, so that's 1 centimeter. The second galaxy moved 2 centimeters. And the farthest galaxy that we started with moved 8 centimeters. It got twice as far away. So that means that we can measure how fast it was going. So if a velocity is the speed, so it's how far it went in the amount of time. So this was all in the same amount of time, 10 seconds. So you can get a calculator. Velocity is just the distance it went over the time it went. There was math today, I didn't warn you about that. But velocity, or the speed, is just how far you go over the time you go. So this one went 1 centimeter in 10 seconds. So that's 1 centimeter over 10 seconds. Which you could put that in a calculator, or you could, if you wanted to, or get a grown-up to help you if you needed, but that would be 0.1 centimeter per second. This one went 2 centimeters in 10 seconds, which is the same as 0.2 centimeters per second. Whereas galaxy C went 8 centimeters in 10 seconds, which is 0.8 centimeters per second. So what this means, oh, there's our universe. Oh, you didn't get to see it fly everywhere. So what this means is galaxies that are farther away to begin with move away from us faster. And this is how we know the universe is expanding, because we can see that things that are farther from us move away from us faster. Now, this is a model. This is a model that helps us explain what's going on. You could also make a plot. So this is something that maybe you can do at home. So you can you can draw a graph of how far the first distance was. This got erased. This should say distance 1 in centimeters versus velocity. And see, the farther something is, the faster it moves. So that's something that maybe you can do at home if you wanted to. But this is something that we notice, that the farther away things are, the faster they move away. Now, the balloon model here that we did is a little, it's helpful because it helps us think about what's going on, but it's not a perfect model. Models are tools that we use to help us think about things, but they are not perfect because our universe isn't a big balloon. We live on the surface. It's in all 3 dimensions. It's a big thing all over the place. So one way that you can do this is you can go bake some bread with little raisins or chocolate chips in it, and you could see the same thing happen as the bread baked. The raisins would get farther and farther away from each other the farther they were from one another at a faster rate. So that's one way you can do it as well. So this isn't perfect, but it helps us think about it. So you can play around with this, maybe draw your dots in different places, do it with more dots, do it with stickers. You can try this out in different ways. But one of the ways that we figure this all out, how we actually measure this, is we can measure, one way to measure distances is with a special type of supernova called a type 1a supernova. And this is a special supernova that has a white dwarf star with a companion star that feeds the white dwarf. So some of the matter falls onto the white dwarf. And then there's a certain point where the white dwarf can't handle it anymore and it explodes. And it always explodes at the same point. And so that star always explodes with the same brightness. Since it always explodes with the same brightness, we know that when it explodes, we can see how bright it looks to us. And so the dimmer it looks, the farther away it is. So that's how we can get the distance part. So one way to kind of see that is I have a flashlight. I shine it right here in my camera. It's really, really bright, and it can be really bright. But here, Veda is going to take it away and walk down our room here. So Veda, can you walk down that way? You can see that as she walks away, the flashlight, it's getting duller, it's getting dimmer. The flashlight is still sending out the same amount of light, but it looks dimmer because it's farther away. So we can use that to figure out how far away things are. But there's something else going on. Because the universe is expanding, we can also measure how fast it's expanding. Okay, thank you. We can measure how fast it's expanding by something called the redshift. So because space is expanding, when this light shines out and the space is expanding, it actually stretches the light waves out, which makes them redder. So we can measure that shift in the red, how much the light gets redder, by looking at the spectra. So we can see how the light spread. We can look at, if we take the light and split it up into its component parts, we can see different things, different features in the spectra, and see how they get shifted into the redder side of light. And we can use that to measure how fast they're going. So these things together help us measure how fast the universe, or how fast things are going, and figure out the universe is expanding. And it was this type of work that back in the 1990s, 2 different teams using the Cerro Tololo Inter-American Observatory, or CTIO in Chile, the Blanco telescope there, they were able to both independently figure out that not only is the universe expanding, it's getting faster in its expansion, which was totally unexpected, and that was a really exciting result. And if you want to learn more about CTIO and all the telescopes in Chile, as soon as we reopen, we're going to have a brand new show that we've been working on. Abrams Planetarium is part of a team with California Academy of Sciences, Astronomy Society of the Pacific, Peoria Riverfront Museum, and the Ward Beecher Planetarium at Youngstown State University, and the Associated Universities Incorporated. We've been making a show called Big Astronomy. We're going to premiere it as soon as we reopen, all about astronomy in Chile and all the different careers that make astronomy happen. So if you want to go follow Big Astronomy on Facebook or Twitter or Instagram, or go visit bigastronomy.org, you can follow all of the stuff that's going on before the show premieres and learn about all the different careers in astronomy that make big discoveries and things like this happen. So there's a lot of careers that make that happen. So if you have any questions, post them in the comments. Thanks for joining us. We have a lot more coming, and thanks for visiting us today. All right, see you later.